Welcome to Archicraft, a bit of architect, your go-to podcast for modern software and solution architecture, enterprise strategies, and AI-powered engineering. Each episode is AI narrated, based on the original blog content by Dima Golodiuk at demongo.com.
You're listening to the second episode of the podcast. This episode is titled, Calculating the Cost of a 70B LLM, the 5-month training run. In this episode, we explore the real-world time and computational cost of training a massive large language model. We start with a simple question. How long would it take to train a 70 billion parameter model on 15 trillion tokens using a cluster of 1,024 H100 GPUs? We'll break down the math from two different angles, using NVIDIA's real-world performance benchmarks and a fundamental FLOPS-based calculation to arrive at a surprisingly solid answer. Let's get started.
Okay, let's unpack this. Have you ever, stopped and wondered what it actually takes to build one of these massive AI models? I mean, not just the code, but the sheer raw computing power and the time involved, because that's exactly what we're diving into today. We're looking at a really hefty scenario here. We're talking training a 70 billion parameter large language model, an LLM on, get this, 15 trillion tokens of data, and doing it all with a cluster of 1024 NVIDIA H100 GPUs. This scale, it's huge. And it really highlights why building these foundational AI models, the ones shaping everything, it's tough. It explains why only a few big players can even really try to make the next GPT or something similar.
It's really fascinating. And our source for this, Dima Golodiuk, isn't just throwing out theoretical numbers, which is cool. They're actually using real-world benchmarks.
Yeah.
And they even give us two different ways to calculate it to sort of cross-check the estimates.
Okay, two methods.
Yeah, which kind of brings up a good point. How consistent are these big, complex calculations? How much can we really trust them? And just quickly on the hardware side, for anyone wondering, these H100 GPUs, they are specifically built for the kind of tensor math, that these transformer models need. And when you hook up 1,024 of them together with super fast connections, like NVLink and InfiniBand, you get an absolute monster of a number crunching machine. Seriously powerful stuff.
Right. So, okay, these numbers are just enormous. Where did Dima Golodiuk even start trying to figure this out? What was the first step to get a handle on this massive scale?
Well, the first approach, and it's a pretty practical one, was to look at actual data. From NVIDIA benchmarks specifically, They use really optimized software, things like MaxText, to get a solid baseline for throughput.
Throughput.
Mm-hmm.
So how fast it can process the data.
Exactly. How many tokens per second this huge cluster can actually chew through. It's a really critical number. And right away, it brings up this trade-off, between numerical precision. You could use something like bfloat16, BF16, or you could go faster with 8-bit floating point, FP8.
Oh, okay.
With FP8, you gain speed, definitely, but you might lose just a tiny, tiny bit of precision. It's a constant balancing act for the people building these models.
Okay, that makes sense. It sounds like a pretty direct way to calculate it. But were there any big challenges or assumptions they had to make for that throughput baseline? Or is it generally seen as a pretty solid number in these kinds of setups?
It's generally seen as quite solid, yeah. These benchmarks are designed pretty rigorously, to really push the hardware to its limits. So based on those benchmarks, for a 70B model running on the 524 H100s, we're talking some serious speed. If you use FP8 precision, you're looking at somewhere around, say, 1.49 million to maybe 1.66 million tokens every second.
Wow.
Yep. And if you choose BF16 instead, which is, like we said, a bit more precise but slower, that number drops to about 1.12 million to 1.18 million tokens per second. Still incredibly fast, of course.
Millions of tokens per second.
Yeah.
It's honestly hard to wrap your head around that kind of speed. But then when you take those rates and apply them to that massive 15 trillion token data set we mentioned, well, those throughput numbers suddenly start giving us a very real sense of the timeline, don't they?
They absolutely do. So crunching the numbers, For FP8 training, the estimate comes out to about 110, maybe 111 days.
Okay, so under 4 months.
Right. But if you go with BF16, needing that extra bit of precision, well, it stretches out. You're looking at closer to 150 days.
It's almost 5 months.
Exactly. And to really nail this down, the analysis did something smart. It cross-referenced these numbers using NVIDIA's own metric. They publish a time to train on 1 trillion tokens number for a Llama 3.170B model. And they report about 7.8 days for FP8 per trillion tokens and roughly 10.3 days for BF16. So you multiply those by our 15 trillion tokens. And guess what? The numbers match up remarkably well.
Really?
Yeah, you get about 117 days for FP8 and around 154 days for BF16. Seeing that consistency across the different methods, it really builds confidence that these estimates are, in the right ballpark.
That's pretty convincing. Okay, so then the analysis switches gears a bit, right? It moves to a different way of looking at it, a bottom-up calculation based on FLPs. How does that approach work compared to the throughput method? Is it like a totally different angle or more of a double check?
It's definitely more of a theoretical check, a great sanity check, actually. See, throughput tells you the real-world speed you might get. FLOP's floating point operations, that tells you the absolute theoretical amount of raw computation needed, like the pure math involved. And for these transformer models, there's a pretty widely accepted rule of thumb. It takes about 6 FLOPs per parameter to process just one token.
6 FLOPs per parameter, per token. Okay, so for our model, 70 billion parameters in that huge 15 trillion token data set. What does that actually add up to? I'm guessing the number is kind of mind-blowing.
You are absolutely right. It adds up to 6.3 times 10 to the power of 24 FLOPs.
Oh.
Yeah, that's 6,300 zettaflops. It's just an astronomical number. It really hammers home the sheer computational weight of this task. Makes you stop and think, doesn't it?
Zettaflops. Okay.
Yeah.
So you have this enormous number of calculations needed. How do you get from that back to actual time? You need to know how fast your cluster can really run, sustained, right? Because I guess you never actually hit the theoretical maximum speed.
Precisely. That's the key difference. So a single H100 GPU might have a theoretical peak performance of, let's say, around 2,000 TFLOPs per second for certain kinds of math. But in the real world, training a complex model like this, you never hit that peak. Never. There's overhead. Moving data around, GPUs talking to each other, software not being perfectly efficient, all that stuff. So a more realistic assumption for sustained performance, for what you can actually get day in, day out on a big job like this, is maybe 50% of that peak. So maybe 1,000 TFLOPs per second per GPU.
Okay. 50% efficiency seems reasonable for something so complex.
Yeah, and then you factor in another thing called Model FLOPS Utilization, or MFU. Basically, what percentage of the time are the GPUs actually doing the math versus, say, waiting for data or doing other housekeeping. And again, for a big, well-tuned system like this, 50% MFU is considered pretty solid.
Right. So you combine that sustained per GPU speed with the utilization factor and multiply by 1024 GPUs. That must give you a kind of effective compute power per day number you can use, right?
That's exactly it. You put all those pieces together, the 1,000 TFLO PS GPU, the 50% FEU, the number of GPUs, the seconds in a day, and the effective daily compute power of our 2024 GPU cluster comes out to roughly 4.42 times 10 to the power of 22 FLOPs per day.
Okay, still a huge number per day.
Oh, absolutely. So then you take the total FLOPs we calculated earlier, that's 6,300 zettaflops, and divide it by this effective daily rate. And that gives you an estimate of about 142.5 days.
142.5 days.
Yeah, roughly 143 days. And what's really compelling here is how close that number is to the throughput estimate we got earlier for BF16 training, which was around 154 days.
Wow, they really do line up well.
They do. It adds another layer of validation, suggesting that whole time frame is pretty robustly estimated.
Okay, so let's bring it all together. What does all this really mean for someone trying to understand what it takes to build these cutting-edge AI models? After crunching all those numbers, tokens per second, zettaflops, we seem to be landing in a pretty specific time window for this huge task.
Yeah, the estimate consistently puts it somewhere in the 4 to 5 month range, squarely in that window. And if you connect that time frame to the bigger picture, well, it really drives home why building these big foundational models from scratch is, right now anyway, mostly limited to a handful of major tech companies and really well-funded research labs.
Because the resources needed are just immense.
Exactly. The cost is huge, not just in hardware, but also in time. And we should definitely remember these are clean, sort of on-paper estimates. In reality, you've got potential issues like optimizing the software perfectly, hardware stability. Can you imagine keeping over 1,000 high-powered GPUs running 247 for months without any major problem?
Oh, man, yeah, no kidding.
Right. And then there are details about the specific model architecture, the exact qualities of the training data. All these things can nudge the actual training time one way or the other.
That's so true. I mean, I struggle to keep my home Wi-Fi going sometimes without needing a reboot. It's not just the raw compute power, is it? It's the sheer endurance needed. The stability to keep a massive 1024 GPU cluster humming along perfectly for like 4 or 5 months straight without major hiccups.
Yeah.
But the analysis did hint at something positive, didn't it? That these times might come down. As hardware keeps getting faster and the software tools get better, these numbers should continue to drop over time.
They should. Which leads to maybe a final thought for you, the listener, to sort of chew on. As this kind of large-scale model training does become gradually more accessible over time, faster hardware, better tools, maybe lower costs eventually, how might that shift the whole landscape of AI innovation? What kinds of new applications or maybe new research directions could emerge when more people, more organizations can actually take on these massive training projects? What happens then?
Thanks for tuning in to Archicraft. This episode was generated using AI from Dmitro Golodiuk's blog at demongo.com/news. If you enjoyed this episode, follow the show on your favorite platform and share it with fellow architects and engineers. Until next time, build smart, architect with intent.